I'm very happy to announce Volker Halbach. So he is both a professor of philosophy in Oxford University, and he is a fellow of New College. So Volker's work is about truths, self-reference, truths and provability. And yeah, I was extremely happy at some point also to collaborate with him on self-reference, truth and provability. And yeah, well, he's generally known for his work. I think he's part of the famous Luxembourg Circle, who is also working on the aforementioned subjects. So yeah, I'm very happy. And so now he's going to speak about self-reference truths. Yeah, the difficult thing is to get the order right: self-reference truths and provability. So
Order doesn't matter.
the floor is Volker's.
Okay, the screen at least. Thank you very much, Albert. I would also like to thank Yong, for organizing this. It's a great pleasure. Normally I would say to be here in Wuhan, but it also does have its advantages to have this online, because otherwise I think we would not have been able, to bring together people from so many different places. Okay, so now I'm going to share my screen. So is this all okay? Okay, so as Albert said, it's about self-reference, truth, and provability. This is a super general title, and I have tried to, focus really on self-reference. What I'm mainly interested in are sentences that make claims about themselves that involve truth and provability. And as Albert outlined, we have collaborated on this, and this talk is to a large extent on this collaboration. So we wrote this paper, a self-reference in arithmetic, which was split by the editor of the Review of Symbolic Logic into two parts, but it's basically one long paper. We also had a more historical paper, the Henkin sentence. And as we just mentioned, I'm working on a book together with Graham Leigh, which is called The Road to Paradox, A Guide to Syntax, Truth, and Modality. And this is also on these themes. In the collaboration with Albert, we did everything in arithmetic. And then with Graham, I'm working on a syntax theory. And the point there is that we avoid arithmetic and give a direct axiomatization of syntax theory. And right now I'm collaborating with Balthasar and Ling Langye, who is also here, I think, on further topics relating to self-reference. And towards the end of the talk, I'm going to talk about what we are doing at the moment. So, but it will take a long time, to get to this point. And here is an overview of what I'm going to talk about. I will have a relatively long introduction, which is mainly informal. Then I talk about diagonal sentences and an attempted analysis of self-reference. Then I talk more specifically about diagonal sentences and Löb's theorem. And then I'm going to talk about the core of Albert's and my paper, which is on Henkin's problem and Kreisel's answer to Henkin's question. This concerns provability. And after that, I'm going to talk about truth, and in particular, truth tellers. So sentences claiming their own truth. Then I'm going to talk about the joint work with Balthasar and Ling Yang, and something I've already done in the joint paper with Albert. And finally, I will have a conclusion which is not really conclusive. Okay, introduction. So this talk is mainly about sentences that ascribe to themselves properties such as truth, falsity, provability, and unprovability. And I introduce some terminology. A sentence that says about itself that it's true is called a truth teller. I mean, I'm not yet saying exactly what these sentences look like. I'm just saying if a sentence says about itself that it's true, then it's a truth teller. We also have sentences that say about themselves that they are not true or false. This is, of course, the most famous kind of self-referential sentence. These are the liar sentences. Then we can also replace truth with provability. So corresponding to the truth teller, we have a sentence that says about itself, not that it's true, but rather that it is provable. And sentences of this kind are called Henkin sentences. And then we take the analog of the liar sentence, and this is a Gödel sentence. So a sentence that says about itself that it's unprovable. And I mean, famously, Gödel, came to prove his first incompleteness theorem by thinking about the liar sentence. And then he realized, one can replace, or truth cannot be defined in arithmetic, but provability can. And by looking at what happens then, he proved his first incompleteness theorem. In passing, I will also consider other properties, other than truth and provability, but they won't play a major role in this talk. Okay, then, just to cover myself, I will use many different phrases to describe a sentence as self-referential. Sorry, I think somebody is not muted. I don't know who. If you could please check. There are other ways, different ways to express self-reference. So I can say the sentence says about itself that it's provable. The sentence states its own provability. The sentence ascribes provability to itself. So these are all Henkin sentences. Or even the sentence says, and then it quotes, I am provable. And these are, for me here, these are just different ways of saying the same thing. So, I will not distinguish between these sentences, even if there might be reasons to do so. And yeah, a sentence saying something about the self, is then called self-referential. But what I'm primarily interested in is what does it mean for a sentence to say of itself that it's provable? Okay, and then the question is, of course, what happens to these sentences? So are these truth teller sentences, liar sentences, Henkin sentence, and Gödel sentences true, provable, or whatever? Okay. Yes. So, I'm now going to show you some sentences that are commonly assumed to be self-referential. And I start with the most famous of all kinds of self-referential sentences, namely the liar sentence. The first one is the sentence that you're reading right now is not true. And this sentence makes use of a singular term, the sentence that you are reading. This refers to a sentence, and that just happens to be the sentence you see on your screen. Okay, then I have a different version, because very often philosophers complain that, this version is actually not very satisfying, because they think, actually, it doesn't make any sense to say of a sentence that it's true or not true. What is true is not the sentence itself, but rather what is being expressed by that sentence. And that is often taken to be a proposition. So you can formulate the liar sentence also if you think that what is primarily true are propositions. And the liar would then look like this. The sentence that you are reading right now expresses a proposition that is not true. So now the property that the sentence ascribes to itself is expresses a proposition that is not true. And the paradox follows in the same way. Namely, the sentence is saying, the sentence that you're reading expresses a proposition that is not true. If the sentence you see holds, well, then it says about itself that it's not true. So, I mean, we have to assume the negation of the sentence that you see, but well, then it does express a true proposition, and yeah, we have a contradiction. People who defend propositions very often claim actually the real advantage of propositions with respect to the paradoxes is that you can say, well, this sentence here doesn't express a proposition at all. I mean, there's no proposition that it's expressed that is true or not true. It just doesn't express anything. If you prefer this solution to the paradoxes, I would reformulate this and say the sentence that you're reading expresses a proposition that is not true, or it does not express a proposition at all. And so if you think this sentence does not express a proposition, well, that's what the sentence is saying. I mean, express a proposition that's not true or does not express a proposition at all. And we have a paradox again. Okay, then here is still another way to obtain the liar sentence. This time I'm using a label L. So I consider a sentence, sentence L is not true. And this sentence, I mean, is just named L. And there's something funny going on. So we label a sentence and then use that label in the very same sentence. And that gives us also a sentence saying about itself that it's not true. Just for variation, here a slightly different version, which I think is a little bit funny. This is, I mean, a curry sentence. If the red sentence is true, then Volker Halbach will become King of England. It might follow that I will become King of England. I think it's clear that it's also self-referential in some sense. But what I find funny here is usually we think of sentences as abstract objects, and I mean abstract sequences of symbols or something like that. But of course, here we make use of the color of the sentence. And if sentences are abstract objects, then presumably they are not red or green or anything. They do not have a color. But sometimes we can make use even of the color of a sentence, like here. But it's just, I mean, to show you some variation. Then, I mean, just to set the stage, I'm not going to say much about this later on. Philosophers got very much interested in self-reference with respect to the paradoxes. And the question was whether we can generate paradoxes without using any self-reference. And as we are going to develop a theory of self-reference, I mean, we would like to apply to these sentences that are claimed not to be self-referential. And so there is, I think, what people now call the Visser-Diablo Paradox. I think my preference, Albert, now is, I mean, to distinguish two paradoxes. I mean, there is here Visser's paradox, and there is Diablo's paradox. I mean, as you can see, the Diablo paradox lacks the indices to truth. Just to see, I mean, how this generates the paradox, I mean, we can go through it. I mean, we look at the first sentence. All sentences below are not true. So assume this sentence here at the top holds. All sentences below are not true. That means this sentence, the second sentence is not true. The third sentence is not true. And you assume the list continues infinitely down. Well, but if that sentence holds, then all these sentences are not true. In particular, then all sentences starting here from the third are also not true, but that's what the second sentence is saying. Therefore, the second sentence is true. So this sentence can't hold. But if this sentence, I mean, fails, I mean, all sentences below are not true, then there must be a sentence that is true that comes below this sentence. And I mean, we don't know where it is, but take, say, this sentence, the third sentence, all sentences below are not true. So, I mean, that sentence must be true. And but now we can run the same argument as before. I mean, if that sentence is true, all below are not true, but then also this fourth sentence is saying something that is true, and we run into a contradiction again. Is this sentence self-referential? I mean, here, I mean, it's not completely clear because it's always the same sentence. I mean, it's just repeated, but we are appealing to a place in this order. And I think Albert's version of this paradox makes it clearer that this is actually not self-referential in a sense to be explained later. Namely, we have true 0, true 1, true 2, and this is a hierarchy of truth predicates. There's one predicate at top, truth not. It applies to sentences containing truth predicates with higher indices. And this is talking about all sentences below. And clearly, I mean, all these sentences are different because they contain different truth predicates. So this is also, I mean, a point where people interested in the paradoxes have discussed self-reference. Sorry, somebody, okay. So in what sense do these sentences claim their own, I mean, all these previous sentences, liar sentences, curry sentences, their own falsity, provability, and so on? I mean, one first strange thing is that only people claim something about themselves. And to say of a sentence that it's claiming something is already slightly odd, I think. I mean, I always complain to my students when they write, this essay is going to claim, this essay is going to say. I find that is slightly metaphorical. I mean, people make claims, whether sentences or essay make claims, that I find that a little bit odd. So I think when we investigate what a sentence says about itself, we should look at, I mean, how people make claims about themselves. And I mean, here are different ways of making claims about oneself. Sorry, I'm using Albert as an example. Albert might say, I'm a logician. Or he might say, the logician participating from the Netherlands is a logician. So as far as I can see on the list of participants, he's the only logician participating from the Netherlands. So in both sentences, he's making a claim about himself. But I mean, in the first case, he's referring to himself via the indexical pronoun I, whereas in the second case, he is referring to himself via definite description, namely the logician participating from the Netherlands. And I mean, in philosophy of language, people have thought actually, I mean, the first kind of self-reference is, I mean, in a way, a better kind of self-reference. Here, Albert is talking directly about himself. And I mean, he will be aware that he's talking about himself. In the second case, I mean, he's just saying the logician participating from the Netherlands is a logician. And I mean, I guess Albert is aware where he's located at the moment. But I mean, that could just be accidentally true. And Albert might not be aware from where he is participating. And I mean, in philosophy of language, there's a famous example of what makes the difference. I mean, this is called discussion about DC beliefs. DC being Latin means about oneself. So we have amnesiac Rudolf Lingens. He's lost in the Stanford Library. So he reads a lot of things, knows a lot, but then Champeri claims he still won't know who he is and where he is, no matter how much knowledge he piles up, until that moment when he's ready to say, this place is aisle 5, floor 6 of main library, Stanford. I'm Rudolf Lingens. So only once he uses, I mean, the first person pronoun, he has really a belief about himself in this first class sense. Yeah, I mean, this is the difference. So in both cases, he's making a claim about himself. But in the first case, when he refers to himself as the man in aisle 5, floor 6, I mean, he just happens to be that man, and he might not be aware that he is that man. And so this is accidental self-reference. And I mean, when he's using the first order pronoun, it's non-accidental, then he clearly is making a claim about himself, because the pronoun I has no descriptive content that can just happen to apply to himself. So I'm just saying this on a background, because this will play a role towards the end of the talk. That, I mean, in philosophy of language, there is an extensive discussion on self-reference, and I think we can glance at it. Although, of course, when we do logic and when we do just philosophy of ordinary English, things are very different. I mean, obviously, in a language of arithmetic, we don't have first-order pronouns. Okay, so, I mean, at this stage, we turn to a more formal setting, and I turn to self-referential sentences in a formal system sigma. Now, first I have to apologize, because I won't be very specific about what the formal system sigma is. So this could be something like piano arithmetic, I mean, but it must contain names for all expressions. But I will make use of function symbols in the language. So it cannot have only 0, successor, plus, times as function symbols. I need more function symbols in my language. I mean, at the moment, my preferred language or my preferred theory sigma would be the syntax theory that Graham, Leigh, and I developed in this new book that we mentioned at the beginning. But basically, I mean, everything we are doing will be very similar. What is different is that if we do it in a syntax theory, we do not have to make use of a coding function. I won't go into this, but I mean, different codings can mess up things in various ways. And I mean, in a syntax theory, we do not have coding in a straightforward sense. Generally, I assume that my theory sigma is sound. I mean, I'm just doing that because in some places I will use omega consistency and other assumptions. And by saying it's sound, I mean, I'm covered against making silly mistakes. Okay, so the most famous application of self-referential sentences in logic is the first incompleteness theorem. And we are going to look at this right now. So very roughly, for any sufficiently strong consistent formal system sigma, we can find a sentence G such that neither the sentence G nor its negation is provable in sigma. And I mean, what we need is the last sentence on this page is not provable in the system sigma, and we need to do that in a formal setting. And I thought I look a little bit in, I mean, how we might obtain such a sentence, first in a semi-formal way, but I mean, it could be formalized in a formal system. And this is something Raymond Smullyan has done in, I mean, a long time ago. It shows very nicely the mechanism at work when we obtain how to obtain diagonalization, in this case via a construction appended to its own quotation. So we look at the sentence appended to its own quotation is not provable in sigma, appended to its own quotation is not provable in sigma. So that's the sentence, and I claim that this sentence, I mean, says about itself that it's not provable in sigma. And we can see this simply by looking at, can mark this. I can look at this definite description, I mean, which is now marked blue. I hope you can see that. And now I simply take that term and basically calculate what expression is denoted by this singular term. So denoted is the term, that's exactly what I wanted. It's this sentence, namely what appended to its own quotations on provable sigma, appended to its own quotation. Well, that's this expression in quotation marks. Here we have a quotation mark, here a quotation mark, and then it's followed by the expression again. And what we can see is, I mean, what I've now marked blue is exactly the sentence above. And in this sense, this sentence makes a claim about itself, says about itself that it's not provable. And this would give us the Gödel sentence, if we can do this in a formal setting. And so we can prove in sigma, if you have this construction available, G, if and only if G is not provable in sigma. Okay. Yes, oh no, so I'm in time, I can do this. Because I'm going to talk about the canonical diagonal operator a lot in what follows, I thought I really introduce it here properly. So this is basically the Gödel construction. I mean, this is much more general than the norm construction, and this is now fully formal. First, what we are going to do is we fix a variable v, and so this will be the variable that is used for diagonalization. Then we need a function sub xy. I mean, this describes a function that takes a formula x and then replaces in x the variable v with the expression y. And we also need a function n, and this takes an expression and returns a name for that expression. I mean, in arithmetic, this will be the numeral of the code of the expression. Okay, now we give a general recipe for how to obtain a diagonal sentence for a given formula phi of v. So our sentence will claim of itself that it has the property expressed by the formula phi. And I mean, you will have seen that before. We have this complex term sub, and now, okay, I should say, strictly speaking, I mean, I need these corners. They take an expression to its code in arithmetic. So, I mean, we have a mapping from all expressions into the numbers. But of course, in order to talk about a number, I need a term in my language, and this is the numeral. And the numeral is simply the successor of 0, and n many successor symbols. So this is a name for this expression in my language. In a syntax theory, we have similar devices. And then I can calculate what this is. So this is the result of substituting in this expression v with the name for this expression. Okay, so we look at this, and now, I mean, in here, we replace this v with this expression. So we go start phi sub, that stays the same, but now we have v, and now this v is replaced with this expression, and then n of v, well, n stays, but then v is replaced again by this expression. So what we have is, we have proved, call this entire thing t. Sigma proves that t is identical with phi of, well, this entire thing here is t. And that way we get self-reference. And of course, we also get the diagonal property. So we have phi of t is equivalent to phi of, well, first we had t, now we replace t with phi of t. And if you call that sentence gamma, we get gamma if and only phi of gamma. What's important for what's going to follow is that we assume that we have sub and n plus all these names for expressions in our language. And I mean, yeah, that's an assumption. Okay, so in order to get the self-referential sentences, we make use of these predicates like provability or truth, and then we need self-reference. And I'm now going to talk a little bit about skepticism about self-reference, whether this is really self-reference in a deeper sense, but it's not only something that some philosophers have claimed, but also, I mean, people who are philosophers and very good logicians. Here we have a quote from Gödel from the original paper. And he says, we thus have a sentence in front of us that claims its own unprovability. So he described the Gödel sentence as a sentence that claims its own unprovability. Okay, now if we look at the first incompleteness theorem, the Leigh paradox and so on, we realize that the only property of the Gödel sentence or the Leigh sentence we use is just this diagonal property. So we just use that gamma is equivalent to not provable gamma. Sorry, I tend to write BEW, which is stands for beweisbar, which is the German word for provable. That's because Gödel wrote in German. I'm German, so I tend to use this, even though it might be confusing. In general, I mean, when you look at some presentations of the Gödel incompleteness theorem, people tend to confuse self-reference with the diagonal property. So I mean, making this explicit would mean we would say gamma ascribes to itself property P expressed by a formula. So think of phi as being not provable. If and only if the following holds, well, I mean, gamma is equivalent to phi of gamma. And usually we expect this to be provable in sigma, otherwise we can't do much with it. And when we do the first incompleteness theorem, many other results, we are just using the diagonal property. And Graham and I have in our book, I mean, a long list of applications of the diagonal property where we obtain many of the traditional paradoxes that people have discussed just by, I mean, applying the diagonal property. Okay. So now I claim, I mean, this is mistaken. Being a diagonal sentence is not the same as being self-referential. I think this is completely clear at an informal level. Namely, if you look at a sentence such as snow is white, if and only if snow is white in quotes is true, that's a diagonal sentence of X is true. But nobody would say that snow is white is self-referential in any way. Snow is white is about snow and being white maybe, but it's not about the sentence snow is white. So if we use truth, then, I mean, truth has, I mean, in the best case, only diagonal sentences. I mean, there's the Leigh paradox, sure, but the truth predicate should have as many diagonal sentences as possible. Not only self-referential ones. And in arithmetic, we can also very easily get diagonal sentences that are not self-referential, unless we do some very strange things with expressing and coding. Take a trivial truth, say a true identity 0 equals 0. That's a diagonal sentence of provability. So you might suspect, I mean, this is a Henkin sentence saying about itself that it's provable if you think being a diagonal sentence and being self-referential are the same. I mean, I will argue, I mean, why this holds, but basically, since we can prove in sigma 0 equals 0, I mean, the right to left direction is trivial and the left to right is just sigma 1 completeness. So the diagonal property is much, much weaker than being self-referential. Okay, also, I mean, we have always, I mean, many diagonal sentences to choose from. So consider the set of all sentences gamma, such that gamma is provably equivalent to phi of gamma. Of course, the set of these sentences is recursively enumerable, but it's never decidable. I mean, for no formula phi. So it's as complicated as it can be. And I mean, if we look at the diagonal sentences that are diagonals, I mean, we replace here sigma is provable with holes in the standard model, then the set of these diagonal sentences is not even arithmetically definable. So there are always many, many diagonal sentences. And I mean, we would like to pick out the self-referential ones. And so I think the connection between diagonal sentences and self-reference is that being a diagonal sentence is a necessary condition for self-reference, at least if we focus on a certain kind of self-reference via closed term and direct self-reference. So we have to choose the self-referential diagonal sentences from these large sets of diagonal sentences. Okay, so in what follows, I focus on self-reference via a closed term. I mean, which is already a problem because in Peano arithmetic or Zermelo-Fraenkel set theory, we don't have closed terms that have this self-referential property, so t equals phi of t. And self-reference via quantification is harder to analyze. There exists some literature on this, but I still find it very confusing. I should also say that I focus exclusively on direct self-reference. What you can have is, say, a sentence A that says about a sentence B that it's true, and the sentence B says sentence A is not true. So we have loops, and sentences make claims about themselves via another sentence, and I'm not going to talk about this. Okay, where are we? Yes, okay. So I'm now talking about, I mean, I think something that is very widespread among some logicians. The skeptic might say what really matters, I mean, is the fixed point a diagonal property of sentences, not the elusive notion of self-reference. That's only for philosophers, I mean, who want to talk about lost ligands and Dessay beliefs. In meta-mathematics, I mean, what really matters is the diagonal property. And according to the skeptic, then there's no role for self-reference in logic and meta-mathematics. Okay, Gödel might have said something about self-reference, but this is only, I mean, as a heuristics, I mean, how he found his diagonal sentence for non-provability. And the skeptic might claim what may create the impression that self-reference is necessary in meta-mathematics is that it's really difficult to come up with a diagonal sentence for this sentence, not provable X. But I mean, Gödel's construction might look self-referential, but once we have that sentence, the only thing that matters is the diagonal property, and we should forget about self-reference again once we have constructed the sentence. And if we concentrate on canonical provability, then actually, I mean, we can forget about self-reference. Now, at this point, I should explain what canonical provability is, which is not easy. Let's say it's the provability predicate defined in Graham's and my book, which is a little bit funny because it's canonical, even though the book hasn't been finished. But it will also, you can also take the provability predicate that you will have seen in an introduction to the Gödel incompleteness theorems in a lecture or a textbook, where people fix a particular system, fix a particular coding, and then define provability in a straightforward way. And then for such a provability predicate, we can prove Loeb's theorem. So we are interested in what happens to I mean, diagonal sentences of provability. Well, they are all provable. And that means, of course, if we have a diagonal sentence of provability, a diagonal phi 1, a diagonal sentence phi 2 of provability, then because both are provable, they are also provably equivalent. So, I mean, this supports the skeptic's view that, I mean, at least for canonical provability, we don't have to worry about whether this phi 1 or this phi 2 is self-referential or not, they are provably, all diagonal sentences are provably equivalent. Okay, so now I claim that canonical provability is actually a very special case. It's an exception. And if we look at other predicates, different diagonal sentences may behave in different ways. And I mean, I will show that, I mean, for some questions, we really need to select the self-referential diagonal sentences and not look at arbitrary diagonal sentences. I mean, unlike as in the case of canonical provability, where they all behave in the same way, different diagonal sentences might behave in different ways. Okay, I mean, in order to support this claim, I will look at provability predicates that are non-canonical. And for this, I mean, I ask you to forget what you know about Loeb's theorem, and we go back to a time before Loeb proved his famous theorem. So we do not yet know that all these fixed points behave, all these diagonal sentences of provability behave in the same way. Okay, so I look at Henkin sentences, and it's very natural to ask this. I mean, Gödel had considered sentences that claim their own unprovability. I mean, as we saw, I mean, Gödel showed the sentence is not provable, it's not refutable. But what happens to the sentence that claims its own provability? I mean, is that sentence provable or not? And I mean, as I said before, a sentence claiming its own provability is called a Henkin sentence. So first, presumably Henkin noted that this sentence is presumably not refutable, simply because if we have a diagonal sentence of provability, if we assume it's refutable, then it's also provable that H is not provable. And that is a consistency claim of some sort. So this probably gets us into trouble with the second incompleteness theorem. So a Henkin sentence will either be provable or independent, but not refutable. Now, Henkin did not ask what happens to a diagonal sentence of provability. And he didn't ask this because he presumably noticed that there are diagonal sentences of provability that are clearly not interesting. So again, we had this example before. Take the sentence 0 equals 0, so a trivial truth, which is provable in sigma. It's a diagonal sentence, but it's in no way self-referential. So, I mean, this shows again analyzing self-reference as the diagonal property doesn't work. And Henkin, of course, did not ask about what happens to 0 equals 0. That's not interesting. We are interested in a diagonal sentence of provability. Well, that's now the problem. It should be somehow self-referential. We want the sentence or a sentence that says about itself that it's provable. So here is Henkin's here's Henkin's question. And so he asked the following in the Journal of Symbolic Logic in a series of questions. If sigma is any standard formal system adequate for recursive number theory, a formula having a certain integer q as its Gödel number can be constructed which expresses the proposition that the formula with Gödel number q is provable in sigma. And then he asked, is this formula provable or independent in sigma? So here, that was my remark before. He asks only is it provable or independent, because he presumably spotted if it's refutable, then, I mean, we are probably in trouble, or that's ruled out by the second incompleteness theorem. And again, he did not mention self-reference in any way, because saying a sentence claiming its own provability was, I think, not precise enough, and he did not have really an exact analysis of that. So he formulated in this way and said, we have a formula, and this formula expresses that the formula with Gödel number q is provable in sigma. So later this was spelled out by Kreisler and others, and we're now going to look at how to understand this formulation. And so what we're interested in is, express the proposition that the formula with Gödel number Q is provable in sigma. And in order to analyze this, we want to explain what it means for a formula to say about itself that it has property P. So what we have is, on the one hand, we have a property. This will be provability in the case of Henkin sentences. And that is expressed by a formula phi. For the moment being, P is provability, phi is simply some provability predicate. I'm going to say more about this later. And then we say a formula gamma says about itself that it has property P if and only if it's of the form phi of T for some closed term T that has phi T as value. So, sigma will prove, if this criterion is satisfied, that T equals the sentence phi of T. Actually, I think I should have overlined this, these corners, because we really won't want the numeral of the code. I'm going to be sloppy about this. And so we have the formula expressing provability. Then we have a term T that refers to that very sentence. And so, it expresses provability. And this is self-reference via a closed term, namely the closed term T. Okay, if a sentence satisfies the Kreisler-Henkin criterion for self-reference, so says about itself that it has property P, then it's also a diagonal sentence. And that's very easy. So if gamma says about itself that it has property P expressed by this formula phi, then it's a diagonal sentence. Proof, trivial proof is gamma must be of the form phi of T, as we noted here. And T has as its value phi of T. Therefore, we have sigma proves this. T equals phi of T. And we start this and then simply replace this T with phi of T. So we get the diagonal property of phi of T. Okay, and this is very much, in line with what we said about informal liar sentences and so on. For instance, when we have self-reference via a label L, so L, the sentence marked L is not true, then the sentence marked L is a term T that refers to the entire sentence. So this is, also satisfies the Kreisler-Henkin criterion now in English. Or the sentence you're reading is true. Well, the sentence you're reading is this closed term T, appended to its own quotation, and so on. All these usual sentence, Kreisler, liar, and so on are self-referential if they are obtained via this closed term. Diablo paradoxes will not be self-referential, but that requires some discussion in the extension of this criterion. The worry is that the Kreisler-Henkin criterion might not be sufficient for self-reference in its full form. So now coming back to Henkin's question, which I copied here again. So what we tried to explain is expresses the proposition that the formula of number Q is not provable in sigma. Well, so we understand expresses the proposition that the formula with Gödel number Q is provable in sigma as is a formula of the form phi of T, where phi expresses provability in sigma, and this T satisfies the Kreisler-Henkin criterion, i.e. we can prove T equals phi of T. It may not be exactly what Henkin had in mind, because he does not say that, we have the self-reference via a closed term, so it could be some quantified formula that also expresses that the formula of Gödel number Q is provable in sigma. Presumably he did that because he was worried we might not have function symbols that allow us to do this in our language. Okay, now there's a big black hole in this talk, namely, what does it mean for a formula to express a property and provability in particular? This is a big topic in metamathematics. Albert has written a lot about it. I mean, Pfefferman, started in 1960 by discussing this and obtained many important results. I'm not really going deeply into this here. It's clear that Kreisel took, understood the expressing a property, he understood this in the following way. So a formula BEW is said to express provability in sigma if and only if it satisfies the following condition. I mean, for all numerals, n is provable can be proved in sigma if and only if the formula with number n can be proved in sigma. So in a nutshell, it's this property. If phi is provable, then sigma proves that it's provable. And I mean, we have assumed soundness for sigma. So if sigma proves phi is provable, then because it only proves true things, phi is actually provable. I mean, this generalizes maybe a little bit because, I mean, we might have provable n if n is not the code of a formula. But yeah, I mean, that's an uninteresting case. So this is more or less how Kreisel understood what it means for a formula to express provability. Okay, now we have everything in place to look at Kreisel's answer to Hankin's problem. So I've copied Hankin's question again, and Kreisel replied to that. We shall show below that the answer to Hankin's question depends on which formula is used to express the notion of provability. So he used, obviously, some non-canonical provability predicate. And here is Kreisel's proof that we can get a provable Hankin sentence and we can get a refutable Hankin sentence. So the first claim is about a provable Hankin sentence. There's a formula BW1 of x and a term T1 of x, such the following three conditions are satisfied. First, this formula is a provability predicate. I mean, obviously that's what we need. This means that this sentence is actually self-referential by the Kreisel-Hankin criterion. We can prove T1 equals T1 is provable. So self-referential says about itself that it's provable in the sense of this provability predicate. And this last line here means that this Hankin sentence is actually provable. This won't surprise you because Lüb's theorem tells us that even for the canonical provability predicate, all diagonal sentences of provability are provable. What is more surprising, that Kreisel also obtained a refutable Hankin sentence. So the same as before, different provability predicate. It is a provability predicate. It is self-referential, so claims about itself that it's provable. But this time, this Hankin sentence is refutable. And I thought we look at the proofs because I think it tells us something about self-reference. This is something Ling Yang and Balthasar are thinking about at the moment. Okay, so we start by fixing some provability predicate BEW. You can take the canonical provability predicate for this. Now we apply the usual diagonal construction to obtain a term T1. But this is not the provability predicate we are after. So we get this T1 equals and then the sentence. Again, I should have overlined this. And only now we define the provability predicate. This is simply obtained by looking at this sentence. Now we remove the first T1, replace it with a variable, and we also replace this T1 and replace it with x. And we say, this is our provability predicate. I mean, first, of course, when we just plug in T1, we get, we can show that T1 equals, this expression. that means we get 2. T1 equals provable 1 T1. Yeah, because here we have replaced now this X with T1, this X also with T1. So it's self-referential. And then we also get 3, because clearly this sentence is provable. And I mean, it's already provable in pure logic. I mean, we don't need any specific sigma axioms. We still need to show that this provability predicate is a provability predicate. But when we look at this provability predicate BEW1, it behaves exactly in the same way as the original provability predicate, with the possible exception of T1. But we already showed if we plug in T1 here, the sentence is provable, and then provable, the sentence, that's of course also provable. So it is also a provability predicate. Okay, so we have verified all 3 conditions in Kreisel's observation, and we have a provable Henkin sentence. Now, what about the much more interesting refutable Henkin sentence? Well, actually, we don't have to go into the details here because it's a very similar construction. Again, we diagonalize. And now this is our provability predicate. And I mean, of course, if I plug in T2 here, then obviously it becomes refutable. So again, this provability predicate behaves exactly like the original one, except when we plug in T2. And yeah, then we can show that this gives us a refutable Henkin sentence. Okay, now the reaction to this was slightly, some sense of disappointment, because people realized that this provability predicate here is very contrived and ad hoc. So people complained that Kreisel had not used the canonical provability predicate. This is of course, the case, and Kreisel himself saw it like that. But what's interesting is that, Kreisel had not only used strange provability predicates, the way he had obtained diagonal sentences is also strange. I mean, they are self-referential by the Kreisel-Henkin criterion, but they have not been obtained by the standard diagonal construction. What we can do is, we can go back to this provability predicate here and apply the standard construction. So the one with sub and then replace the numeral in the sentence and so on. And this will give us a different term, T3. And of course, T3 will be different from T2. And what's important here is that T3 is somehow obtained by doing something with this formula. So T3, when I dig my way into these quotations in there, will contain T2 in some way. And so T3 is more complex, will have a higher Gödel number under certain assumptions than T3. And so if I apply the standard diagonal construction, then actually I can show, again going back, if I plug in T3 here for X, that's then true, and I can simply forget about this. This chunk and everything depends on whether T3 is provable in the original sense, and then Loeb's theorem strikes, and actually we obtain a provable Henkin sentence. Okay, where are we? Okay. We have now 2 diagonal sentences. This sentence with T2 and T3 both say about themselves that they are provable using the same provability predicate, but we are using different terms, T2 and T3. One is refutable, one is provable. And I mean, that's somehow puzzling. So what we have is that not all diagonal sentences of this provability predicate that satisfy the Kreisel-Henkin criterion behave in the same way. And I mean, what has bothered me and others is, should we be more interested in, when we ask about what happens to the sentence that claims its own provability in the sense of this provability, should we be more interested in this sentence obtained by the standard diagonal construction or in Kreisel's sentence? And the suspicion is, I'm going to say more about this slightly later, is that this diagonal sentence is slightly better because of reasons to be explained. So we need to be careful in the analysis of self-reference. And I mean, just asking what happens to the sentence that states its own provability in the sense of this, well, it might depend on which self-referential term we use. Okay, so whether Kreisel's Henkin sentence is provable or refutable does not depend contra Kreisel only on the provability predicate. It also depends on how we get self-reference. And so the answer to certain questions depends not only on the coding and the formula expressing provability, that's well known, but it may also depend on how exactly we obtain self-reference. And of course, people forgot about, I mean, this kind of self-reference because they turn to canonical provability, and there all these differences disappear, and we can forget about intentionality from self-reference. Okay, so what we might ask now is, can we obtain a refutable Henkin sentence using the standard provability predicate? Basically prove what Kreisel had claimed to have proved. Maybe we didn't say that. And Albert succeeded in showing, yes, we can. But I think I don't have too much time, so I think I'm going to skip ahead and skip this proof. Summary of Henkin sentence. If a canonical provability predicate is chosen, all diagonal sentences of this predicate are equivalent. There are provability predicates that have refutable and provable Henkin sentences that have there are provability predicates that have refutable, but also provable Henkin sentences. I mean, this was the example of this provable 2 provability predicate. We just did this. I mean, something I'm not going into is we could now also look at the situation for Henkin sentences if we express provability by Rosser provability, and I mean, something is known about this. And basically, it depends on how exactly we define Rosser provability. Okay, now returning to the main thread of our discussion is the skeptic might say, don't fuss. I mean, all the diagonal sentences of the canonical provability predicate behave in the same way. And I mean, nobody really except some philosophers care about this strange provability predicate. Self-reference doesn't play any role in proper metamathematics, as I said before, and we should forget about self-reference. And actually, Kreisel himself was, I mean, tried to forget about this his old paper and said, I mean, Lüb's theorem, that's the solution. Now, this skeptic position about self-reference fails for truth. I mean, we can concentrate on canonical truth predicates, and their different diagonal sentences behave in different ways. So let me just look at the time. Yeah, okay, I'm doing okay. So let's say sigma is a truth predicate for sigma n if we can prove the key sentences for all phi in sigma n. And now sigma n is a certain complexity class, which we will be familiar with, namely say, I'm going to concentrate on sigma 1 in particular. This sentence is sigma 1 if it contains only bounded quantifiers. Only at the beginning, it has one unbounded or may have one unbounded existential quantifier. And I mean, sigma n with larger n just means one unbounded existential quantifier at the beginning, then an unbounded universal quantifier, and you just count the number of unbounded quantifiers at the beginning of the sentence. And I mean, the reason for restricting, of course, focus to sentences of a limited complexity is because we cannot define a sigma that is a truth predicate for all the sentences. That's Tarski's theorem on the undefinability of truth. But we can define truth predicates for sigma n sentences. Actually, in addition, we may require, so there should be an R here, not a T. We might require that we can also prove that, say, a conjunction of two sentences is true if both conjuncts are. And we might also allow free variables in here. So phi is true of x if and only phi of x, and so on. But I just concentrate on the T sentences. Now, what's interesting is that one can prove that there is a sigma 1 truth predicate, and this truth predicate itself is sigma 1. So, but it cannot be of lower complexity. This means if we tried to build a liar sentence using a sigma 1 truth predicate, we would fail because we would have to negate this sigma 1 truth predicate, and negating a sigma 1 sentence gives you a pi 1 sentence when you pull out the existential quantifier over the negation symbol. It becomes a universal quantifier. So we cannot construct liar sentences, but we can construct truth teller sentences. Now, what's completely different from provability here is, I mean, when we look at, first, when we look at arbitrary diagonal sentences, there are many diagonal sentences, and they do not behave in the same way. For instance, 0 equals 0, that's of course a sigma 1 sentence, no quantifier whatsoever, but also 0 is distinct from 0, trivially disprovable sentences. They are both diagonal sentences, simply because, I mean, they're just instances of the T schema. And so in contrast to provability, different diagonal sentences behave in different ways. So now we can ask, what happens to the sentence that states its own sigma 1 truth? Clearly, I'm not asking about 0 equals 0 or the negation of that sentence. What we want is somehow it should be self-referential. And one way, to ask that question is, okay, what happens if we apply the canonical diagonal construction that I showed you to this sigma 1 truth predicate? So I abbreviate this as true sigma 1. So this is a sentence gamma obtained by the standard diagonal construction, and we get gamma if and only if true sigma 1 gamma. What about that sentence? Of course, this already holds because it's a T sentence, but it's really the specific construction that makes the truth teller special, not that it's a diagonal sentence, because there are many. Okay, so we can look at that sentence, and what Albert proved is the sigma 1 truth teller is actually refutable. So the canonical truth predicate, true sigma 1, this is of the form there is a y theta of yx. There are different ways to define this, but think of this as somehow saying there is a verification. It's basically you have a compositional or a Tarskian definition of truth. You start from atomic sentences, and then, you might combine connectives, you have bounded quantifiers, and then there is a y means there is such a sequences of sentences that increase in complexity that has x as its final output. The usual way would be that y is a sequence of triples, formula, then a variable assignment, and then the third entry keeps track of the truth value, so it would be 0 or 1. And I mean, if you choose that truth predicate, then we can construct the canonical diagonal sentence. I mean, actually, it only needs to satisfy the Kreisler-Henkin property, and then we can show this truth teller sentence is refutable. So here we have a result with a natural predicate, the sigma 1 truth predicate, where we really need to insist on the Kreisler-Henkin property because arbitrary diagonal sentences may behave in many different ways. Okay, in order to prove this, we need to make an assumption, namely in general, if we have a sigma 1 sentence, there's a v sigma v, and we have this property down here. So that means if y is, I call it a verification sequence for this existentially quantified sentence, then somehow y must contain a sentence or a variable assignment that contains a witness for this existentially quantified sentence. And but because y, I mean, contains only this, this witness, the witness itself will be smaller than y. But this depends on how we carry out our sequence coding. I mean, depending on exactly how we define the sigma 1 truth predicate, may depend on the sequence coding, the way we code sentences, and so on. But somehow the idea is, I mean, the v that we, if it exists, that must somehow be contained in y, or a bigger witness must. Okay, I mean, with that assumption, we can actually show that the sigma 1 truth teller is refutable. So the truth teller is of the form, I mean, will be of this form. There is a y, y of t, and t is now a term denoting this very sentence. So we have this. And now we can prove this. I mean, we reason in PA. Suppose we have, there is a verification of t. Then we choose the smallest the smallest such y. This is y naught. So we have this. Y naught is a verification sequence, and there is no smaller. That's just our choice of the smallest. So because we have t equals this is the self-reference property. So this is where we really use the Kreisler-Henkin property. The assumption above combined with I gives us there is a set smaller than y naught theta set t. So this is exactly what we have here. So we get a smaller witness. But of course, we have assumed y naught is the smallest witness, so we have a contradiction. And therefore, that means our assumption was false, and we can refute the sigma 1 truth tell. We can refute this sentence. Okay, so we get the sigma 1 truth teller is refutable. So I'm going to skip this. I mean, under suitable assumptions, we can generalize this. Sigma n truth tellers are refutable, pi n truth tellers are provable. This is something that's in Albert's in my paper. Graham and I mean, have done this also for syntax theory. So where it becomes interesting, because there the monotonicity assumption is something that is built into the syntax theory. So in a way, I always thought what makes looking at truth tellers so interesting is the situation is very much like in the case of provability before Loeb's theorem. So before Loeb's theorem, people thought, oh, well, I mean, whether a Henkin sentence is true or not may depend really on some arbitrary decisions. It may depend on small inessential details, whether the Henkin sentence becomes provable or not. So that was Kreisel's attitude. But then Leigh proved no, all diagonal sentences are provable. And then, I mean, all these worries disappeared that accidental features might play a role. In the case of truth, there's nothing like Leib's theorem. And so, I mean, yeah, these accidental features, I mean, may play a role, and our results are not very robust. And particularly, they depend on assumptions such as the one here, which, I mean, has to do with how exactly we code up things. Okay, then, I mean, I would like to mention, I mean, how much, the status of a truth teller sentence can vary by looking at different ways to obtain truth teller sentences, namely by using different truth predicates. What we can use instead of the partial sigma 1 truth predicate that I've just shown you, we can use a provability predicate for a finite subtheory of Peano arithmetic. So let this be a provability predicate of some finite subtheory of PA that, I mean, is strong enough to prove sigma 1 completeness, basically. Then Peano arithmetic will prove this. And this means, of course, that this formula is a provability predicate. So why can Peano arithmetic prove this equivalence? Well, first, the right to left direction is just sigma 1 completeness. We would be able to prove this already in I sigma 1 itself, and definitely in Peano arithmetic. And the left to right direction, this is really a specific property about PA, namely PA proves the reflection principle for all the finite subtheories. So yeah, I mean, that's the reason why we cannot replace PA here with I sigma 1. Anyway, so we have now a different truth predicate for sigma 1 sentences in PA. What we can also do is we can use a truth predicate of an axiomatic theory of truth, I mean, a new primitive truth predicate. We could use the compositional theory of truth, or we could use the Kripke-Pfefferman theory of truth. And that gives us 3 different sigma 1 truth predicates. And funny enough, all these truth predicates are in some way natural. They are not like this Kreisel construction where we say and X is distinct from T1. They are all defined in a fairly straightforward way, but they're sentences that claim about themselves that they are true, i.e. sigma 1 truth tellers, behave in very different ways. And also what we need to assume about self-reference is a little bit, depends. So we can show that every diagonal sentence of the canonical sigma 1 truth predicate is refutable in PA and definitely, I mean, a stronger axiomatic theory of truth. What we need as an assumption, we need, I mean, what we call the assumption, I mean, monotonicity, but we also need that the truth teller satisfies the Kreisel-Henkin criterion for self-reference, of course. Now, if we use this provability predicate as the truth predicate, then we get a provable truth teller. So exactly the opposite of the one above. And I mean, what we added is, I mean, if we take the canonical diagonal sentence of the primitive truth predicate of an axiomatic theory, then depending on how we set up things, we will get probably something independent. I mean, basically diagonalizing will, I mean, get us out of the appropriate category of sentences. Yeah, so we have 3 more or less natural sigma 1 truth tellers. One is refutable, one is provable, and one is independent. So these results about truth tellers are highly unstable when we compare to what happens to the Henkin sentence. So saying about oneself that it's provable is much more stable than saying about itself that it's true. Okay, so now at the end, I'm going to talk about what I called uniformity in this old paper with Albert. And this is, I mean, all very dodgy, but I think it's philosophically very interesting. I mean, again, we concentrate on self-reference via a singular term, not via quantification. We look at, I mean, a sentence that ascribes to itself a certain property needs to be a diagonal sentence as before. It also should satisfy the Kreisel-Henkin criterion. Yeah, okay. But I mean, even if we have diagonal sentences that are self-referential by the Kreisel-Henkin criterion, there may be differences. So above we had a Henkin sentence, this Henkin sentence, that's refutable. That Henkin sentence is provable. Both are built from the same provability predicate, but this one was obtained by this just plugging in T2 into the provability predicate, whereas here we applied the canonical diagonal construction. And when we ask, well, what happens to the sentence that ascribes to itself the property of being provable via this specific provability predicate? Is that sentence provable or refutable? Well, the answer is, well, it depends on how exactly we obtain self-reference. And so, I mean, my intuition is, and that's now controversial, I mean, obtaining self-reference via the canonical construction seems to be more relevant or more interesting. So if I'm being asked, I mean, do we want this sentence? When we ask about the sentence claiming its own provability or this sentence, I would say, well, that sentence is more interesting. So this is joint work with Balthasar and Leigh. Okay, I've tried really to boil this down to an extremely simple example. Namely, I mean, you remember that Kreisel had this constructions of provability where he said, well, x equals T2 or blah, 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 blah is provable. Now here we just concentrate on identity. So we have a sentence A, and the sentence A is just this. A is identical with A. And we have a sentence B, and the sentence B is identical with A. Now I claim by the Kreisel-Henkin criterion, both sentences claim about themselves that they are identical with A. It's just that here in the sentence A, we are using that very label A in order to talk about A, and here we are using B. So, I mean, both are diagonal sentences of X is identical with A. But in a way, I mean, we have just used this different labels. Yes, so, and of course, I mean, the first one is a true sentence. The second one is a false sentence, obviously. And my feeling is that, I mean, the truth of this sentence, I mean, depends on choosing a very specific term that refers to itself. And my feeling is what is, I mean, a better way of self-reference is, I mean, not exploiting the specific property of A. I try to explain this using a truly philosophical example. So we are considering a person claiming about themselves that they are thinking. I mean, so René Descartes might say, I'm thinking, and Georg, I mean, Georg Kreisel might say, the person thinking right now, he is thinking. In a way, both refer to themselves, but the second is more accidental, and that leads then to this insight that, I mean, uniqueness apart, that the second one is trivially true. I mean, the person who is doing the thinking is thinking, sure, Whereas I'm thinking, I mean, René might be doing something else. So here we get self-reference by using a term that has no descriptive content. Here we get self-reference via this term, and that has a descriptive content, and then we use that descriptive content which trivializes the second sentence. Okay, so when we ask about self-reference and self-referential sentences, self-reference should be obtained in a non-accidental way. So, I mean, in the best case, we would use indexicals such as I and me. And as rigid designators, they just refer to the speaker without mentioning any specific properties of the speakers. I mean, that's what makes them DC claims. I think I'm going to skip the Mary example, but go now to arithmetic. What we would like to do is we would like to mimic this use of indexicals in the language of arithmetic. And I think our best way to do this is we would like to get rid of all the accidental features of how we obtain self-reference. So if we have to use in our result, I mean, a very specific feature of how we obtain self-reference, then that's not first-class self-reference. And my idea was we can get rid of these accidental features if we obtain the self-referential sentence by following a specific uniform method that always gives applied to arbitrary formulae a self-referential sentence. So how did we obtain the bad self-referential sentence? There should be a lower index 2 here. We just plugged T2 into a provability predicate. That was Kreisel's trick, but that does not follow a uniform method. The uniform method would be just to apply the usual canonical diagonal method or something like that. Okay, so we are now looking at diagonal operators, and just to mention this definition, a diagonal operator is a function that gives applied to a formula with a fixed variable a diagonal sentence of phi x. And of course, we assume that our diagonal sentences satisfy the Kreisel-Henkin criterion. We are here not interested in any other. Okay, so what I thought in the original paper, I think is not really interesting. So uniform self-reference, I mean, must be explained by, I mean, making clear what a uniform method is. And Ling Yang has, I mean, done some work in this direction. Namely, I mean, we make it explicit what it means to apply a uniform method. Namely, a diagonal function must be defined from certain operations, substitution, taking a canonical name, I mean, Gödel numeral. We might take, I mean, Boolean connectives, function application, predicate application. But it's not some arbitrary primitive recursive function that gives us the diagonal sentence. In particular, what we cannot do is make a case distinction. Namely, for this formula, oh yeah, we carry out the diagonalization in the following way, but for a different formula, we do it in a completely different way. Now it has to bring out this uniformity. And if we set up things in a certain way, we can actually show that, I mean, just plugging in, I mean, T2 in provable 2, that's not uniform. Applying the canonical diagonal construction is uniform. And I mean, what does come up here is some monotonicity property again. So that's, I mean, as far as we have come so far, so this is going on. So the upshot of this, sometimes we can prove a result for all diagonal sentences, such as in the case of canonical provability. Sometimes we need to assume that the fixed point satisfies the Kreisel-Henkin criterion. So for instance, standard provability, standard sigma 1 truth is an example here. But sometimes, as in the case of this Kreisel provability predicate, the Kreisel's Henkian criterion is not sufficient. We can still get different results. And in that case, I'm more interested in a uniform diagonal operator, which corresponds somehow to the use of a personal pronoun such as I. Yes, okay, just summing up quickly. I mean, self-reference is highly elusive. People talk all the time about it in the theory of paradoxes and in meta-mathematics, but it's really not completely clear what it is. I mean, this is only self-reference via closed term, so self-reference via quantification is still a wide field. I haven't said anything about that. I have not said anything about what it means to express a property. Again, there's a lot of research about this. And the problem of self-reference also interacts with these other problems. Okay, and last slide. Yes, I would like to, just ask a few questions that are open. So are there more interesting natural predicates where the Kreisel-Henkin criterion makes a difference? So more like sigma n truth predicates? Then more interesting, are there more interesting natural predicates where even when we have the Kreisel-Henkin criterion, we get different results and we have to insist that our fixed point must have been obtained in, or diagonal sense must have been obtained in a uniform way? Then still very dark is which role plays monotonicity of the coding in its various forms. And I mean, in particular, can we get rid of this assumption? And then last but not least, I mean, maybe we can dodge many of these problems concerning coding by moving from arithmetic to a syntax theory that would get rid at least of the problems from coding. But even in a syntax theory, self-reference remains elusive. And I hope you're still there, and but that's the end of my talk. Thank you.
Okay, thank you very much, Volker, for your talk. So now there's room for questions. Please. Oh, yeah, Balthasar has a question.
Thanks, Volker, very much. That was super interesting. I have a small question about you had like 3 truth tellers, and one was provable, one was refutable, and one was independent, right?
I bring up the slide.
Yeah, I think that would help. Great. So I was just wondering about the independent one.
Yeah.
Yes, perfect. Okay, so CT is a typed theory here, right?
Yes.
So my worry would be that I find the other 2 examples natural, even though I'm also not very sure. So there are 2 issues. The one is if like the probability predicate for I sigma 1 really counts as a truth predicate. Of course, it does according to your definition, because there I think you call the truth predicate any like formula which satisfies phi if and only true phi, or phi being a certain class of formulae. So I don't know. I would be skeptical whether I would like want to require more about a predicate to really count as a partial truth predicate. That's one issue. The other one, maybe more severely, is here that the situation in the case of the independent truth teller seems a bit like when we take a liar sentence from a partial truth predicate. So we get outside the class, we get outside of the scope of the truth predicate, right? So in that case, our truth predicate is actually not sensible anymore, like, or doesn't sensibly apply anymore to the truth teller obtained in this way when we use the construction using CT. Because
yes.
Okay. So I understood correctly. Okay.
Yes, you understood it correctly. So in a way, the last one is least interesting.
Yeah, exactly. Okay.
So I mean, what bothers me is, I mean, we can ask which truth predicate is now the most natural. I mean, is it this true sigma 1, or is it this provable in I sigma 1 predicate? And I mean, one way to explain what it means for a formula to express provability is to say, well, the formula just mirrors the meta-theoretic definition of the property. And how do we define sigma 1 truth? I think if I had to explain what sigma 1 truth is to my students, I would not give them this predicate here. I would simply say, well, it means the sentence is true and it's sigma 1. And that looks as if sigma 1 truth is being defined from a primitive, I mean, a truth predicate that is unrestricted. And so, I mean, starting with a primitive truth predicate, I mean, is closer to the usual meta-theoretic definition of sigma 1 truth. I mean, where we start with a big truth predicate and just restrict it, unlike, I mean, in this predicate. Does that make sense, Balthasar?
No, that totally makes sense. So I agree that this approach is more natural, but then the question is, then maybe we just can't have truth tellers. Like if I would really require that when we speak about truth tellers in an interesting way, that the truth predicate really applies to the truth teller.
Yes.
Right.
Yes,
yeah.
yes. Okay,
so,
yeah.
but it totally makes sense. So I fully agree with the approach or the idea behind it. I don't know. Maybe there are other questions. Thanks. I have another question, but maybe I'll ask it a bit later about the partial truth predicate.
Sure.
I can. Okay. Now I can see more. I can see Graham. So Graham, the floor is yours.
Thanks. Thanks, Volker. So maybe I just want to follow up on what Balthasar just said, because if I recall correctly, I put it like this because I know it's in our book, but you wrote this part of the the book on this the case of the three truth tellers. CT can be replaced with a type 3 truth theory, right? KF, for example.
Yes. So
all we want is that these are all equivalent for, say, sigma 1 formulas, right?
Yes. So yes, and I mean the version of CT I had in mind was in a way type 3. I mean, it must not contain an axiom saying only T3 sentences can be true. So yes, I mean, it can be type 3.
Because then it makes sense to ask about the truth teller in KF, and we know that the canonical one there is also independent by
yes
the arguments. Yeah.
Okay, that
so
should have been my answer to Balthasar.
So I wanted to check that we weren't missing something there. So my main question is what we learned from this analysis. I mean, there's you mentioned the kind of conclusion that canonical provability is robust, and in some sense, anything else we have looked at does not exhibit robustness to any to any kind of degree like that. But what conclusions should we draw from that kind of observation, would you say?
So say from the robustness of provability.
For example, yes. I mean, so we've learned this about these predicates, but kind of what next?
So what next is, so I mean, as I see the historical development, of course, after Gödel proved his incompleteness results, everybody was interested in canonical provability, and rightly so. That's obviously, a very important topic. But by concentrating on provability, people forgot about the notion of self-reference, because it simply disappears when we concentrate on canonical provability. And so what I'm interested in is, investigating self-reference in a purely arithmetical framework. And, but for that, we ask what Henkin tried to ask: what happens to the sentence that states its own provability, just for other predicates? And then we realize, in contrast to canonical provability, we need a robust notion of self-reference. So one hope would be, so for instance, when we look at sigma 1 truth tellers, somehow we get an answer to an arithmetical truth teller. It's refutable. And this runs against the usual story you will get in the theory of paradoxes, namely the truth teller is gappy or something like that, just like the liar sentence. But we are in a purely arithmetical framework, and they're the sentence either true or false. And so my hope was that by looking at this in an arithmetical framework, we can learn something about what happens to these circular sentences, but that requires, an explanation of the notion of self-reference.
I guess perhaps with the partial truth predicates have a stronger statement, right? That not only are they true or false, but you actually get provability or refutability.
Yes. Yeah. And this is, many people working on the paradoxes find this puzzling. These are legitimate truth predicates. They're defined in arithmetic. They have been used in meta-mathematics for a long time, and there we can study the truth teller sentences. And strangely enough, it might become very, very fiddly. Small decisions can make a big difference.
Okay, then now the floor is to Ye-Ling Yan.
Hi, sorry. Hi, Volker, can you hear me?
Hi, yes.
Yeah, okay, sorry. Okay, I'm also wanted to ask about the three truth predicates. So from my point of view, the second one, using a provability predicate, is kind of more accidental than the other ones, because you specifically mentioned that this is a property of PA, right? You can prove the reflection principle of the finite subset theories. So I just want to ask: is there kind of more these differences between the robustness of the truth predicates you define, and at least the second one can't define for a weaker theory, for example? So I'm just thinking about the kind of the uniformity of these three provability predicates.
It's of course, the partial truth predicate in a way also, kind of exhibits features of a provability predicate. In a way, they're not so different. The big difference is, I think, formally, that this kind of truth predicate is like provability, but like cut-free provability. So, that was exploited in the proof that the truth teller is refutable. So if there is a proof, it must contain a witness for the sentence. That is not required in this notion of provability. That might be a cut, and we might arrive at the sentence by all kinds of things, but by assuming it's negation or something like that.
Right.
So,
yes.
I mean, so I think they're actually very similar. And I mean, yes, you're right. I mean, probably this is a little bit more robust. What I miss so much is, I mean, a way of saying a formula expresses a certain property if this and this condition is satisfied. And now you seem to be saying, okay, yeah, I mean, it should be more robust and not depend on the strength of the theory or something like that. Yeah, maybe. Anyway, both are truth predicates in the sense defined above.
Right. I'm not saying that like we should like finding truth predicates that does not depend on the theory, but I mean just so in general, I think the philosophy like we're looking after here is for example, why the canonical provability predicate can yield so robust results. Like you can define the canonical provability predicate for various drastically different theories, for various different codings and numeral functions, and also so in some sense, the robustness there like kind of hints at the robustness of the result it can be. So technically, I'm thinking at, or I'm assuming that is that if we can do a construction more robustly, or we can vary it to a greater extent, then there's more hope that we can get more robust result, like you hoped, I think, maybe.
Yes, and okay, and in this sense, I mean, using this truth predicate looks more robust. Yes, but I don't think that being able to carry out this, I mean, say the construction of provability for many theories, independent of coding, independent of the theory, my feeling is still that, I mean, that we get these nice results, and Lüb's theorem for provability depends on the specific notion of canonical provability. Ling Yang, would you say, I mean, I can define Rosser provabilities, take some specific version of Rosser provability. That's the construction of this is also extremely robust. I can do it for arbitrary codings. I can do it for arbitrary theories, just like standard provability. But then the results are very unstable.
I agree, yes, of course. But I mean, I think they're slightly more complicated there, because for the Rosser probability predicate, you have a relation, right? You need to specify a relation in the second clause, and there you can do different things.
Yeah.
And some results in the literature depends on the specific choice, right? Because, for example, Ross's provability predicate can't satisfy all of derivability conditions, and some doesn't satisfy the second one, some doesn't satisfy the third one, and that depends on the choice you make there. So I mean, I'm not saying, so there's not the Rosser provability predicate, but we have the canonical provability predicate. So
yeah, but I think it's an illusion to think there is the canonical provability predicate. That you can also make many choices there. And I mean, take different textbooks. No textbook will give you the same provability predicate. But it seems there different choices don't make a difference. And we have the feeling there are inessential deviations from the same definition. And in the case of Rosser provability, we have a different feeling, but I don't think it's more than a feeling.
So yeah, I totally agree with this. And I think, so there is some hope, and I think we might try this to formalize this feeling like more explicitly. Yeah.
But But yeah, I mean, you know, Balthasar and I have been working on formalizing our feelings for some years, but we have failed to express our feelings so far.
Okay. Okay. Yeah. That's all my question. Yeah. Thanks.
Thank you.
Okay, there's still a question by Balthasar.
Right, so I get to ask my question about the partial truth predicate. This is actually a follow-up what you just spoke about the robustness of the sigma 1 truth predicate.
Yeah.
And there's a very natural alternative how we could set up a sigma 1 truth predicate. And I was wondering if Albert, you or Graham ever thought about it. So basically, this truth predicate is like that X is like equals to like existential quantifier, then a variable, and then a matrix A, and A is delta 0. And then we just say, well, there is a witness D such that the result of substituting D for the variable Y in A is sigma, is delta 0 true. So we use a truth predicate for delta 0 truth. And so in that case, we don't get the assumption which is used in the result of your joint paper. And I was wondering if you thought, so I think this is a very natural example of a truth predicate, and like really seems to be a natural alternative to the version where we quantify over the sequence of triples. And I was wondering if you looked at it, if you tried to squeeze out some properties there.
So I mean, we have talked about this. This is really a question for Albert and Graham, right?
So yeah, but so what? Oh, am I mute? Yeah. So what does the delta 0 truth predicate look like?
Okay, I mean, you can that, for instance, there you can quantify over a series if you wish.
Because
Sorry,
the witness for it should be sensitive to the parameters, right?
So the delta 0 is a fixed truth predicate, right? And we just plug in the witness of we just substitute the witness for the variable and then check whether the result is delta 0 true.
Yes.
Okay, in this case, it would really help to show it on a blackboard.
But yeah, okay, well, yeah, precisely because the truth predicate for the delta 0 is of course itself sigma 1, and so
yeah, exactly.
Also, so you have two witnesses, right? So the witness for the truth and the witness for the substitution. Well, yeah, we should look at this at the blackboard. So
would be very interesting to if we've got some results there, because as opposed to the case of, let's say, the probability predicate, there I would really have this very strong intuition that these are just both very natural formalization of the same meta-mathematical notion.
Yeah. Mm-hmm. And of course, different. I mean, we have this assumption, and it's somehow related to monotonicity of coding. And I mean, for different truth predicates, we might need different assumptions about monotonicity. So, I mean, a very natural assumption about monotonicity is for expressions. So whenever you have, say, a code for an expression, and that expression contains the standard name for another expression, then that standard expression has a code that is smaller than the expression of the big code. But we might also need monotonicity for sequences. So if I take a sequence and suddenly the sequence has a smaller code than one component in the sequence, that also sets up or might make the result fail. And I think you can tweak it in many, many different ways. And in a way, I think, Balthasar, is that right? I mean, I could start to come up with a notion of monotonicity that would make your construction I mean, because you have this delta 1 truth predicate that mentions, I mean, the witness. And that should somehow boost up the complexity in some way. So this should be disallowed in some way. So our hope would be, I mean, this is also ruled out by some monotonicity constraint.
Okay, I think that would be interesting to actually try to spell out. I don't see that immediately. But
yeah, I mean, it might be a very unnatural monotonicity constraint.
Yeah, right. Okay, yeah.
Well,
Thanks, but that's it.
We should check the Putlack, the Hayek and Putlack book where delta zero truth predicate is spelled out in great detail, so we could really see what the whole thing, what your proposal looks like. It's now.
Okay, thanks. Yeah, thanks.
There is a question still by Graham. Is that true, Graham?
It is, well, yeah, a comment mainly. So okay. I too have, it happens, I too remember having this discussion, I think even possibly between the three of us about this truth predicate. I don't remember the result for the sigma 1, but I think it has the same result, but it depends highly on how one formulates the delta zero truth predicate. But I think that when we think about asking the same question for higher partial truth predicates, so sigma n truth predicates, then it becomes very difficult to reason about the nestings of quantifiers within codes, and that a nice simplifying situation to first consider is that we'll consider a sigma n partial truth predicate for pre-next sigma n formulas.
Yeah.
And now one can define this truth predicate more or less in the way you said, by just explicitly giving quantifiers at the front. So it was in that context that I recall us discussing it, but I don't even recall whether we worked anything out about the pi 2 level or not. So
I mean, basically what we did is, I mean, we just I mean, for sigma n with n bigger than 1, I mean, we just said it's also refutable, but basically by lifting the assumption up to the higher complexity level. And I mean, it's not completely clear whether then the assumption is as justified as in the sigma 1 case. And I mean, for pi 1, I mean, we simply assumed, I mean, they are the negations of sigma 1 sentences. So the higher, I mean, you're right, the higher we climb, the more assumptions we have to make. And I mean, at least speaking for myself, I'm much less confident about the required assumptions than for the sigma 1 level. And if you drop these assumptions, I think nobody really has a good feeling for what happens.
So I think the question of whether what would be a natural partial pi 2 truth predicate is what would constitute a natural partial pi 2 truth predicate is very unclear, and saying that this truth predicate starts with the universal existential quantification and then checks some quantify-free matrix or something, that is perhaps harder to justify than in the sigma 1 case.
Yes.
Okay, there's still room for some very quick question. We still have 1 minute.
Anyway,
I mean, I could.
Okay.
Yeah, no, go ahead.
Yeah, I ask a quick question. You claim that according to the Kreisler-Hinking question, the Diablo Paradox is not self-referential. So is any criteria under which the Diablo Paradox is self-referential?
Yeah, well, I mean, there was one suspicion, namely, I mean, first, looking at the Diablo paradox as presented in my talk, namely simply as an infinite list of sentences, that's dodgy. So people thought, okay, if we do it properly in arithmetic, we will have to use the diagonal lemma in order to obtain Diablo's paradox. And Gray and Priest pointed this out. And then he very quickly reacted by saying, oh, we need the diagonal lemma, therefore it's self-referential. So, I mean, I would send you to, I mean, if you're interested in a defense of the claim that Diablo's paradox or Albert's paradox is still self-referential in some way, then the place to start would be Gray and Priest's paper some years ago. And so, but I think there's a mistake there, namely, oh, we use the diagonal lemma, therefore we have self-reference. I think that's too quick. Personally, I believe it's not self-referential.
Okay, so you see that self-reference depend on the coding and how to express the property and the Fisa property. So it's all these factors which influence the self-reference. Is any other factors for the influence of the self-reference?
Yes, yeah, I mean, there are all these factors. I mean, what I haven't talked about at all is the problem, I mean, how coding influences self-reference. And I mean, simply because I wanted to keep this out of the talk and not open another can of worms. But I mean, Albert's has, I mean, a couple of different codings with built-in self-reference. So where we really have suddenly we can prove in the theory n equals phi of n, and n is just a numeral. And I mean, if we do self-reference that way, we can even get self-reference in piano arithmetic, which we usually cannot in the Kreisler-Henkin sense in piano arithmetic because we lack the function symbols. So yes, I mean, all these factors come into play. So sorry, did that really answer the question, or?
Yeah, my question is that only these three factors influence to decide?
Only,
yeah.
I'm just wondering what else could come in. I mean, another factor is, I think, that might come in is how we think really about syntax theory. And I don't mean how we code syntax, but we can understand syntax in different ways. And I think how we think about syntax is even more basic than the first kind of intentionality, namely coding. So we might think of a sentence as a tree. We might think of a sentence as a sequence, a linear sequence of symbols. And this, or I mean, how do we think about variables, for instance? That's also maybe not clear from the beginning. But these decisions are at the very beginning, even prior to coding. And if we change anything there, it might have a knock-on effect later on. But I haven't looked at it, so I don't know.
Okay, thank you.
Okay, well, I think this discussion could go on. We already progressed to the next subject, so to speak. Yeah, so maybe it's a good point to thank Volker again for what